how we can figure out our rate constant k, which we need to basically determine the gradient. So the approach would be that we use this equation here that we've derived earlier, and we are trying to create a model and then refine this model. And in order to use this equation, we need to figure out what is our final concentration of the GFP, and that's pretty simple. We can make a rough estimate for this final concentration, and we just simply pick one of these values here, because that is pretty much what we would see when we go back to our graph, and that is the final concentration. So let's just simply say we pick one of those. It does not need to be terribly accurate at that point, because we will let Excel do all the heavy lifting. So let's say we go here for 11,000. That is a good starting point here. And for the rate constant, we just simply use an arbitrary value. Let's say we use 0.1. We could choose basically any other value because this will then be optimized through a program that Excel has built in. Now let's create this model and let's calculate our concentration of the P at various time points if we use these values. So we just use the Excel function, and we say equals this value here, this for the protein concentration, and we lock the cell by clicking on F, pressing F4. We see the cell is locked now, times open bracket 1 minus, and E is exponent of negative, that is our K here, that's this value, and again we lock this value by pressing F4, times the time here that we have, and then we need to close this bracket for the exponent, and we need to close the bracket, and that looks pretty good. So what have we got? Okay, we've got 0 here, which is not terribly difficult because we've got a 0 here. And now let's see what the other predictions are. So here that would be the predictions, and what we see is probably not a terribly good prediction. What we can do is we just simply plot these data here, and the corrected as well as the model, and let's see what this looks like. So insert, and we go to the scatter graph and this one here. So here we have the corrected data. These are in blue, and this is our prediction for the model. And we see it's not a very good model. We've got this huge hump here, but we can do something about it, because what we can do now is we can calculate what actually is the difference between our corrected data and the model. And what we do is we just take the square of the differences, because then it doesn't matter what we actually, whether it's positive or negative. So here we just simply take the difference between the corrected, so difference between corrected minus the model data, and we square that. Squared. So for each data point, we now get basically the square of the difference. And we pull that down. That's this one here. And that shows us the square of the differences for each data point. And what we can do is we can also create a sum and basically add them all up here. And that is our sum. And that's a pretty large number. Now, ideally, what we want to do is we want to change these parameter at the same time so that our model looks much more like our corrected data. So let's put, well, let's go down and say 0.01. Let's see if this model then looks a little bit more like our data. And what we see here is now the curve has shifted, and by just changing this, and it looks more like the model. But ideally what we want to do is we want to get it as close as possible. We could, for example, change this value here. We might want to change this to 1000. Let's say 1700. Let's see what happens if we change it like that. No, the sum gets bigger. Now, what we can do instead of this trial and error, we can use the built-in function for Excel, and that is what is called the solver function. So you go to data here, and you go to solver. And what we will get is, let's just simply make these a little bit, let's see what we've got. So the solver asks us, what do we want to achieve? We want to set this objective, that is here our sum here. We want to have this sum as small as possible. We want to set this to a minimum, because if this sum is very small, it means that there is not a huge difference between our model and the actually measured data points. We want to change these data points here, the final protein concentration and the rate constant. We want to change that at the same time. We want to make any unconstrained variables non-negative, and otherwise this looks pretty good. So we've got this one here, we've got this one here. We want to set this to a minimum, and now Excel will try to optimize these data points, these two parameters at the same time. Let's see if we can come up with a solution. So Excel says it found a solution that brings that to a minimum, and we just simply say yes, okay. And we've got a change in our data. And if we are now looking at the curves, our model, that's the yellow curve, and the blue curve are very, very close together. So we have calculated with our model a sort of a trend line, if you like, that is very close to actually the observed data. And even more importantly, we've got a rate constant that we can use for this equation. And if you remember, we said we want to evaluate here the gradient right at this point here. So right at the beginning, that gradient, and we set this gradient, dp over dt, that's the gradient, that's our production rate, dp over dt, equals our concentration that we get up here times the rate constant. And the rate constant here, of course, that would be in second to the -1 because that is a rate constant for a first order reaction. So what we get here now for the gradient really is exactly these two numbers that we are looking for. So for this gradient, we just simply multiply these two numbers equals the concentration times the rate constant. So that gives us a gradient of 155. Let's round this a little bit, 155. So that would give us 155. And what is that? That would have the units of RFU per second. And if we want that in, let's say, in minutes, we can just simply multiply this number by 60. So that is this number times 60. And we got roughly, we would get roughly roughly 9,200, so roughly 10,000 RFU units per minute. So that would be our gradient right at the beginning of the concentration, at the time point when we start the reaction. So we've got this gradient here. Now we need to convert the RFU units into something like mole or something like that. And how we can do that, that will be discussed in the next video.